Hello, I am Frits de Mul, and this talk is about the magnetic field of a rotating homogeneously charged sphere. This presentation is part of a series of presentations about electromagnetism. The B field of a rotating homogeneously charged sphere. We have available a charged sphere with total charge Q and radius r, and it's rotating with omega radians per second. The question is calculate the B field in arbitrary points on the axis of rotation inside and outside the sphere. So, let's calculate the B field in a point P outside or inside the sphere and assume the z-axis is through O and P. And we have coordinate systems x, y and z, but better is coordinate systems r, theta and phi. Analysis and symmetry. The volume charge density is Q over 4 pi r to the third power over 3 coulomb per cubic meters. And the rotating charges will establish a volume current through the sphere. The volume current density J in amperes per square meter will be a function of r theta. We start with Biot and Savart law. dB vector is mu naught over 4 pi times the current times dl factorial product with ER over rp squared. Rp is the distance between the element in the sphere to point P. Element in the sphere to point P. This is Rp, and this is on the element is on a distance r from the origin, the midpoint of the sphere. dB, dl and ER are mutually perpendicular. dl, ER, dB. The direction of the contributions dB is that we have cylinder symmetry around the z-axis, and it means that we only need the z component. First, an intermezzo, a long wire. Biot and Savart here, mu naught over 4 pi, dl times ER over 4 rp squared. And we note that r and factor ER are necessary. This is r, rp, and factor ER. dB is perpendicular to dl and ER. dB is perpendicular to the plane and the triangle AOP. Let's have a volume current here. Then the volume is the current density is amperes per square meter here inside the volume, and this is dA and this is dl. This is the element dl and this is dA. And dA times dl is dV. dV is the volume element. Again, dB is perpendicular to dl and ER, and thus dB is perpendicular to the triangle AOP. Back to the sphere. Two circles at a ring at radius r form a ring, and here this is the base of the volume element. We have a homogeneously charged sphere with a volume density given here, Q divided by the volume, and we have a volume element given by r d theta, that is r d theta, r sin theta d phi, r sin theta d phi, given by r sin theta here, and dr. That's the volume element. dr times r d theta times r sin theta d phi. Here is the situation again. Here we have dA. The current is going through that volume element. And here we have the current density through that volume element dV. Surface dA. Charge rho dV in dV will rotate with omega radius per second. And we have dV is dA over times dl. dl is given by r sine theta d phi, and dA is dr times r d theta. We need expressions for J, ER and RP. Here is the situation again. What we know already is dV, dl and dA. And now we know that the charge in the torus with radius r sine theta and cross-section dA, this torus here, with cross-section dA and radius r sine theta, that charge is rho times 2πr sine theta times dA. 2πr is the radius, 2πr sine theta is the radius, is the circumference of the charge of the torus. We have a full rotation in 2π over omega, and this means that the current is rho times 2πr sine theta dA over 2π omega is rho omega r sine theta dA. And the current density is rho omega r sine theta in amperes per square meter. Amperes per square meter going through that element. Now, we know J. We know J is perpendicular to ER, so the factorial product will be J itself. And we know dV, r d theta, r sine theta, d phi times dr. Now we know almost everything. We know J, we know dV, we know that there is cylinder symmetry, and it means we only need the z component, and the z component is given by cosine alpha, and cosine alpha here is r sine theta over rp. The only thing we need to know is rp. Again, dB, J, dV, the cosine component, and now rp. And rp here is given by r sine theta squared, r sine theta squared plus zp, is this zp, minus r cosine theta squared. This is r sine theta squared. And this is the total expression, mu naught over 4 pi times rho omega r sine theta over, that is the J, current density, rp squared in the denominator, then dr times r d theta times r sine theta d phi, that's the volume element, and here is the component along the z-axis. This is the expression again. Rp is given in this expression. Integrate here will give you this integration between the limits r and 0 and r for the radius, 0 and pi for theta, and 0 and 2 pi for phi. The result when performing the integrations is 2 mu naught r omega rho omega r to the power 5 over 15 zp to the third power. And this result holds for zp larger than r. For zp in between minus r and plus r, the result is given in this way here is mu naught r omega r to the third power divided by 15 times zp to the third power times 5 r squared minus 3 zp squared times ez. And for the other zp below the sphere The B is the same as on top side, but with an extra minus side, of course. Here is the result again. And for set B smaller than R. And B points along EZ for all points everywhere on the Z-axis. When we introduce the volume density, then we can rewrite this expression with R to the power 5 to this expression here with R squared and the Q. And this is the result for ZB smaller than R. Here we have the figure of the homogeneously charged sphere. For Q is 1, mu naught is 1, and omega is 1 in SI units. This is the expression for radii larger than R, for distances larger than R, and this is the expression for distances smaller than R. So we have these expressions here for the homogeneously charged sphere, and in another presentation we derived these expressions for conducting spheres. For a conducting sphere, the field is larger outside the sphere, but inside the sphere we have a homogeneous field. And for a homogeneously charged sphere, the field outside the sphere is smaller, but inside the sphere the induction is mostly larger than in the case of a conducting sphere. And this is the end of this presentation. Thank you very much.